Okay, this is a continuation of lesson 6.5. This is the third page. We usually don't have a third page, and I ran out of time on the other one, on the other film, or whatever, video. So we're going to look at this example. So exponential example problems. We have some that are just going to be plugging in the numbers, some that are word problems, and then we're going to look at comparing between linear and so this is going to be pretty important. So let's look at how to solve these. It says evaluate each function for the given value of x, which means when it says evaluate, that means they give you all the information and you just do what we call kind of a plug and chug. And you just know how to work the order of operations. So we have y equals -2, that's your a, times 5 risen to the third power. Now remember when you do PEMDAS, you do the exponent first. Don't make this -10 cubed. It's cubing the 5 and then multiplying by -2. So 5 cubed, you're saying -2 times, now 5 cubed, I know it's 125 just because I've worked with this so much. If you don't know that by heart, you can do 5 times 5 times 5, 3 times, or 5, your exponent key, to the third power. Okay, so it's -2 times 125, which that's going to be y equals -250. Whoops, sorry. All right, this one. So this is a growth, which means like after 3 days, if it's multiplying by 5 every time, after 3 weeks, whatever the time is, then it's going to be at a -250. If it started at -2, and then it's going to end at -250, whatever the scenario is. This one, it's starting at 3, whatever it is, but it's going down by half, -2. You can't have like -2 days, but we'll come up with solutions. So you're saying a -5 to a not -5, I'm sorry, 5/10 to a -2nd power, which that means, okay, so we got to think about how this is going to look. 3, now 5, this is like 1/2. Think of that as a fraction. So maybe think of this as a fraction to the -2nd. We did this actually on the other page. So a -1/2 to a -2nd means you're going to, the negative, you're going to reverse or do the reciprocal. So you're going to have 2 squared. So if you do the reciprocal, it makes that exponent positive. So you're going to have 4. So 3 times 4, this is going to be 12. Okay, I know we'll probably need to do more practice with that. Well, let's move on to a word problem. Using a model with the exponential function. So oh, sorry, my dogs, of course, are going to bark right now. So suppose 30 flower beetles. I don't even know what flower beetles. Oh, God, I hope they're not our flower. I don't even know what those are. Every time I talk, he barks. Sorry. I'm going to shut my door. Hold on, guys. Stop. Okay, I apologize. It just gets hot in this room. Okay, so flower beetles left undisturbed in a warehouse bin. Ooh, gross. The beetles population doubles each week. Okay, so we start with 30 and it doubles each week. So the function, so they already go ahead and tell us 30 is where it's starting. It doubles each week. Give the beetle population, how many beetles will there be in 56 days? Okay, well, it wants to know in how many weeks. That X represents weeks. You've got to make sure you watch that. Don't put 56 in for that X because that's going to be a large, large number. I don't even think your calculator is going to do that. But it's 56 days. So how many days are in a week? Are 7. So 56 divided by 7 is 8. So your X is going to represent 8 weeks. Okay, so then once you know that, then you have 30 times 2 to the 8th. Okay, 2 to the 8th. I do not know that by heart. So 2, exponent key up here, 8 equals 256. So you have 30 times 256 times 230, 7,680. So there's going to be 7,680 of these beetles, which I'm going to look up what a flower beet. Oh, I spelled it wrong. B-E-E-T-L-E-S. So 7,680 beetles. Gross. It is what it is. Okay. The graph represents the bacterial population after X amount of days. So if in science they talk about growing bacteria, and this is a great example of exponential function with bacteria. So write an exponential function that represents the population. Ooh, okay. So we've got to look at, in order to know, so remember our function was a, b, x. So our a is our starting point. That's the y-intercept. So, okay, look at the ordered pair. They tell us. There's no way we could look at that and know that. So they tell us. So 3 is our starting point. Here, this is what I'm going to do. We're going to have to find the difference. I would do when x is 0, y is 3. When x is 1, y is 12. X is 2. Maybe you're going to start seeing it here. 3, 192, and then 4, 768. Okay. So our a, our starting point, our y-intercept is 3. Now, how is it changing? Visually, we can tell it's exponential just because, look, it's curving. So it's exponential, and it's going up, it's increasing. But what's happening here? How does 3 become 12? How does 12 become 48? Well, you're multiplying by 4. So the function to this is going to be, you can do it in function form or with y. 3 times 4 to the x power. The x represents the number of days. So after 3 days, it was 192 bacteria population. Okay, 764. So it grows exponentially. So here's our equation. You could write that, or as a function if you want to write this way. That's fine too. Okay, now find the population after 12 hours and 5 days. 12 hours and 5 days. Okay, so you could do this 12 hours and 5 days. Well, that'd be like 5.5. So I'm trying to think of the best way for you guys to do this. Oh, you know what? You can do 5.5 in your calculator. So you can do this. Y equals 3 times 4, 5.5. Because we can do 4 to the power of 5.5. 2048. No, is that right? Oh, wait a minute. I'm reading the problem wrong. It says after 12 hours and 5 days. So I can see this. This is a bad worded problem. Because in my mind, I would have done 5.5. Well, what they're looking for is 2 different answers. Ooh, careful. All right, so if 12 hours. 12 hours is a half. So we're going to do 3 times 4 to the half power. Remember, half power? So this is like 0.5 or half power. Remember how you do that? 4 to the 1/2 power is the square root. So you can do 3 times the square root of 4, which is 3 times 2. So that should be 6 for 12 hours. So 12 hours, it's going to have 6 whatever population. Now 5 days, 3 to 4 to the 5th. Now 4 to the 5th is like 16 times 16, which is, so you can do 4 to the 5th. It's 1024 times 3 is 3072. That's right. So 5 days, 3072, 12 hours, it's just 6. So actually, think about this. If it's starting at 0 and in 1 day it goes up to 12, well, half a day it's going to be 6. Well, I could have done it that way. But now another way you can do this, if you don't remember the fraction, you could have put 4 exponent half there, and it's going to give you 2. So there's multiple ways you can do that. All right. So again, if you're like, oh my God, I'm so confused, we'll do some more practice. There'll definitely be a Delta Math. We'll do some more practice with this. Okay, now we want to talk about the difference between linear and exponential. Linear and exponential. So this is going to be huge once we also do our quadratics of knowing the difference. So linear, when you have a table, you're going to either add or subtract to get the constant rate of change. Okay, so you're going to add or subtract by the same amount every time. By the same amount every time. Okay, so it's going to be the same amount. It's a common difference, not a common ratio. So this is going to be a common difference. And when it's graphed, it's going to be a straight line. If I can spell straight correctly. Straight line. So when you graph it, it's going to be a straight line. Exponential, when we go from one to another, it's going to be multiplying or dividing. Multiply or divide by the same amount. Now, we call this a common ratio because it's really a fraction. I'm trying to write too fast. Common ratio, and then it's going to be a curved line. So exponential, terrible curved line, but it's going to be a curved line. So, and we'll have more practice on identifying linear, exponential, and quadratics too. So here's an example. Here's one's written as a table, and we're going to determine if it's linear or exponential, and then we're going to write a function rule. It's been a while since we've done this for linear. So we got to look at, first of all, these are going up by 1. That's good. Now what's happening here? We could say multiply by 2, but that's not happening here. We're adding 2 each time, okay? So it's like 2 over 1. Your slope, remember your slope, is 2 over 1. So this is a linear function if it's adding or subtracting by the same amount each time. Remember our y equals mx plus b, where we have y equals, the slope is 2, your x, and your b is your y-intercept. When y is 0, or x is 0, the y is your y-intercept. Okay, so it's been a while since we've done that, writing a slope-intercept form based on a table. So we found the slope, then we found where the y-intercept was, so your slope and your y-intercept. Now, let's look at for exponential. What's happening here? Okay, it's multiplying by 2 each time. Now remember our formula, y equals ax, or ab to the x power. Our a is your y-intercept. So your a is 4. Is your common ratio, what's being multiplied by. Now make sure you don't put 42. Be very careful how you write this. Don't write 42x. So your final one is this. So it's 4. That's your y-intercept. What is it being multiplied by every time? Is 2. Your x represents the number of days, hours, whatever it is. Okay. So we'll do more practice on determining between linear and exponential a little bit later.